Welcome one and all. Welcome to the day 4 session of Design for 3D Printing. I am P. Jackson, Department of Mechanical Engineering, Aditya University. In yesterday's class, you have learned how to design and design for 3D printing, how to use Tinkercad and other prospects. Today, in today's class, in the first session of the class, I'll be giving you what a 3D printer is, what are the basics of a 3D printing is, what are the capabilities and the limitations of a 3D printer, and in the second part of the session I'll be giving you different defects, how they are generated and why they are generated, and this few remedies from my side. It will be a class which will lead you to a super finished or a good 3D print. So let's start the session. Let's get to the PowerPoint. As you can see on my screen, there are different types of 3D printing technologies available, and these are the few of the examples where we have material extrusion, we have vat polymerization, we have material jetting, binder jetting, powder bed fusion, direct energy deposition, and sheet lamination. All these 3D printers are industrially used, but as far as our discussion is concerned, and most of the uh, educational institutions are concerned, material extrusion is the most popular and most widely used. In the metal extrusion, there are two different types of FDM technologies. Technologies which are your FDM, fused deposition modeling, and your FFF, which is fused filament fabrication. Uh, FFF is the most popular because it is user friendly and also the pocket friendly version of FDM. It was generated as a part of RepRap technology, which was initiated by the bunch of professors and students from MIT, and this gave the opportunity for various companies like Ultimaker, Prusa, and all to make desktop 3D printers, and the technology is also free, open source, so it is widely available. So the main part of our discussion will be this FFF technology, wherein I'll be giving you the various intricacies or various factors which affect the quality of the 3D print, and by the end of this class I might be helping you to give out a few parameters of how to use this technology. As technology is developing, all the technologies have their limitations and strengths. So even FFF have its own limitations and its advantages. So main advantage is it's open source and it is freely available and it's quite cheap when compared to other printing technologies. Whereas its limitations are concerned, I'll be getting in deeper into the limitation part because at the end of the session on day 6, we'll be printing some parts or we'll be discussing how to print some parts on this FFF technology itself. So what are the limitations? The limitations are quite many, but these limitations has to be incorporated into your design before you get into the print. So there are some parameters which cannot be printed using the FFF technology, and let's discuss them in detail. So as you can see, FFF technology is basically a filament which is passing through a heated nozzle. It is getting into a state of viscosity wherein it is deposited in the form of layers. Once these layers get deposited, it is cooled by a fan and and it is deposited in the form of a solid block. So there are many parameters that you need to consider before getting into the 3D print, or before giving the 3D print we need to observe many things. The first one is your extruder. So this particular gears are usually connected to a stepper motor which controls the inflow of the spool or the raw material. Right. As the filament is flowing in, this flow is usually controlled by this extruder motor. So next comes the heating element, which is at a particular temperature, which is set to a particular temperature, and this temperature is usually dependent upon what kind of material you are using and what kind of properties that material have. Then we have a fused filament. There should be a strong bond between these two layers. There should be a strong bond between these two layers, which is a thermomechanical bond, and this bond plays an important role. And the distance between the layers or the thickness of the layers is called as your layer thickness. This will affect the finish of your print. And the other factors are your crosswinds or the ambient conditions of the print, which ambient conditions which also affect the condition of the print, and the type of even that first layer which is deposited on the bed, and the bed temperature will also affect the print. Uh, so before getting into the serious discussion on the FFF 3D printing, we need to understand that this technology was developed by some students and professors, and they have to make it cheaper or to make it low cost, they have made few adjustments, and these adjustments need to be considered before giving into the design of the 3D print. So there are some limitations that need to be followed, and if you are pushing over this limit, the print may not be good. So before getting into the 3D printer, or a good looking 3D print needs the following parameters. It needs a good design. It needs a good design. It needs correct settings in your slicing software. It needs proper calibration of your 3D printer, and after all, even after all these are good, you need to do some post processing. So we have already discussed how to model the 3D printers, 3D models, and now we are going to understand what are the parameters that you need to look into before you give the design for the final print. So when you see the wall thickness, so wall thickness plays an important role while doing the 3D prints, as the wall thickness is one of the important parameters, and the most used nozzle, most of the 3 FFF 3D printer is 0.4 mm. So all the defects that I am going to discuss in the coming presentation is keeping this 0.4 mm nozzle diameter into consideration. If you are using some other nozzle, I'll give you some tips on how to use it. So usually the wall thickness should be at least twice. So the wall thickness should be at least twice the nozzle diameter, for a reason that the slicing software that we use will usually remove some fine details for the sake of convenience. So if you are making your wall too thin, there might be a chance, or there will be a chance, like this thin feature will be taken as a minute feature, and it may get neglected, and you end up with a print which has no walls. So usually the thumb rule is like you should have at least two layers to make it prominent, and you, as the thickness of the wall is equal, as the thickness of each wall is equal to the diameter of the nozzle, is equal to the diameter of the nozzle. So it should be at least twice the nozzle diameter. It can be any more, but it should be at least zero point 0.8 nozzles. So having a thick wall has its own constraints that I will discuss later. But nozzle, the wall thickness should be at least twice the nozzle diameter. So if you are using a 0.5 nozzle, the wall thickness should be at least 1 cm, 1 Next comes the bridges. So bridges are the features where the printer is printing between 2 points in air. So if the distance is more, there is a quite a chance that this print which is being printed in the air before getting cooled down may get sagged. Before getting cooled may get sagged. So if this sag happens, the whole print may lose its finish or its prominency or dimensional accuracy. So it is usually suggested, like if you want to bridge, or if you want to make bridges like this, or if you want to print a bridge, it should be a maximum of 10 and it can be a maximum of 15 if you have a good cooling system. So the maximum bridge that it can print is FFF print can print is 10 to 15 If it is more than that, you can have supports. Supports. The next thing is the overhang. While the bridging is printing in the air between 2 points of the at the same height, whereas the overhangs is printing in the air between the 2 points which are not at the same height but at a inclined direction. So this inclination the 3D printer can do is a maximum of 30 degrees. So you need to understand that before you give any overhang in your 3D print, it should be a maximum of 30 degrees. As you can see, the overhang angle is this angle from the vertical, not from the horizontal. So this is 30 degrees. And in few FFF printers where the cooling system is a dual cooling, or the cooling system is finely tuned, it can go up to 45 degrees but not more than that. So before giving a overhang, you need to do some testing on your 3D print that I'll discuss in tomorrow's class. Once the testing is done, you can go for the angle that your printer can print, but it is usually a minimum of 30 degrees and a maximum of 45 degrees. Anything over it will need some supports to be printed. The classical exam, there is an example on the board, like if you want to print this particular features in this direction, so let's see the possibilities. So if you want to print a T, you can see that this particular surfaces are clearly in air and the angle is definitely greater than 30 degrees and there is no support underneath. So this will definitely, this particular print will definitely fail. Coming to the H, uh, these two pillars will have no problem to print, but the horizontal member, if this distance is less than 10 mm or equal to 10 mm, this will have no problem for printing. But if is more than 10 mm, this might have a problem, or this might face a little sag. This might face a little sag. E is definitely not possible because there are surfaces which are perpendicular to the horizontal. So this by beam might not be have any problem, but the horizontal, all the horizontal members, these two horizontal members without any support will definitely not print. Coming to the Y, as the angles are almost equal to 30 degrees or less than 30 degrees, if the angles are somewhere around 30 degrees or less than 30 degrees, this Y will have no problem in printing, and this particular Y will definitely print easily. So this is the scenario of overhang. Try avoiding overhangs as much as possible, and try to see that the print have low overhangs, and if you have, try to avoid the bridges. Even if you have the bridges, try to make them as small as possible. Next comes the hole. These holes are usually not as the most of us observe that the holes that we would like to print will not have the same diameter as we have mentioned in the design. There is a particular reason. There is a particular reason, like when we print the print in layers, when we print the print in layers, there is a pressure from the nozzle. There is a pressure from nozzle which pushes the material in downward direction, and due to this, the material will expand. And due to this expansion, usually it will expand on the open side rather than the side which has material. So due to this expansion, usually the whole material expands and the hole becomes smaller than expected. The hole becomes smaller than expected. So usually if you give 2 mm hole, it will make a 0.1 mm hole. So it is preferred that you need to understand how much this expansion is happening on your printer. You need to take few measurements and correct your design accordingly so that your holes are correct. So if your printer is generating a mistake of 0.2 mm, you need to add 2 mm to your design, wherein your holes will be to the correct dimension. Next important thing is the way you are, or the orientation you are printing the part. So usually we prefer to have at least one flat surface on which your 3D print has to rest. If you and according to this orientation, any print is possible. Like I have discussed in the previous slide, how this T is printing T and E is not possible. But as you can see, if I change the orientation of the print, now the T, if T is resting on its horizontal member, it is resting on the horizontal member. Now there is a quite a good chance of printing it. H without any overhang can be printed because all the surfaces are on the ground. E can also be printed because now the horizontal surfaces are vertical surfaces and only horizontal surface is resting on the ground. And as usual, Y even having overhangs can also be printed. The next part is bottom surface. I have already told you like the surface is plays an important role. So there is this defect called surface shift. I'll be showing few examples of surface shift in the coming session. These surface shift usually occurs due to the reason like the area of contact between the 3D print and the bed is not enough. So if you have enough surface contact area between the print and the bed, then this particular defect is minimized. But if you are using anything of this orientation or this orientation where the surface contact is not enough, you might face some problems. There are some particular techniques where you can avoid this problem, but as far as the design is concerned, try avoiding this problem so that other techniques need not be used. Next, the orientation part. So usually the 3D prints are weak along the printed layers, but they are good enough to take the load perpendicular to the layers. As a reason, like the material strength will come into play. Here the strength that is or the load or the stress that 3D print can take is the maximum bond strength. Where here the material properties will take its place. So usually before the printing, you need to see that on in which direction the print is happening and use the orientation. You use the orientation in such a way like the load should always be perpendicular to the layers. The load should always be perpendicular to the layers. So this is one of the design considerations that you need to take or you need to give before you print the part. Next comes the text size. So text size is usually everyone wants to brand their 3D prints and text size plays an important role. So the blind mark is like it is almost equal to your wall thickness. Keep in mind that the text should have uniform text should have uniform thickness and should be at least twice the nozzle diameter for a simple reason like for a simple reason that I have mentioned. If the features are small enough, your slicing software will eliminate it or remove it, and the depth of the text should be at least 2 times the layer thickness. Right. So next important design parameter that you need to observe when you are designing for a 3D print is the corners or the edges. So there should be no sharp edges because of the reason, like when your nozzle is moving, you need to understand that this nozzle has a weight to it and is moved in x and y directions using a stepper motor. When you have sharp ends, when you have sharp ends, as you can see that the nozzle has to take a sharp 90-degree turn where inertia will come into play, and due to this inertia the belts or stepper motors will face the problem, and you might end up with a shaky or vibrating 3D printer. So it's the inertia which is kicking in. So I suggest to give a small chamfer at each and every corner at least 0.2 mm, wherein the smooth motion will cause this inertia to come down and have a good print. Shaky and vibration 3D printer will cause ghosting and other defects also. I'll be discussing in depth in the next topic where I'll be discussing various defects and why these defects happens, and I'll be giving you few tips how to avoid this defects. Next comes the features, might be the holes, might be the chamfers, might be other features that you want. Keep in mind that these features will also be eliminated during the slicing, or these might not be printed because stepper motors are not as accurate as DC motors or servo motors. So see that all the features that you want to see on your printer should be at least 2 mm or above. The features should be either it may be a hole, a notch, or any other features. These features should be more than 2 mm. Anything over 2 mm will not have any problem. Next comes the pins, which are important. So these pins have a small diameter and a long length. So see that the nozzle, if the pin diameter is less than 3 mm, it is usually weak and breaks easily, or it might not print effectively. Whereas coming to the pins which are up 3 to 5 mm, they're of average quality. They may or may not take some load. Usually, it is observed that if it has more than 6 mm of diameter, 6 mm of diameter, the quality is good and strength is also good. The one thing that you can do to give it some strength, either you can provide some chamfer at the bottom, chamfer or fillet at the bottom, or you can provide it some ribs. So yes, so if you're providing it with chamfer, it will have better addition to the main part. Either it may be a hole or a shaft, and chamfers will always play where the horizontal, where you need some strengths. So ribs, fillets, and chamfers will provide you a good strength in case of a vertical members. Coming to the mating part, mm, theoretically, the hole and the shaft of same diameter will fit. But as far as your fitting is concerned, if you want to parts which has to fit like a glove, you need to see that the hole and shaft should have the margin of at least 0.3 mm on each side. Like in the example that is shown on the screen, the whole shaft or the square hole shaft is 10 mm, whereas the square hole is 10.6 mm, which is giving out 3 mm on each side. So this gap is need to be at least 0.3 mm for the perfect fit. And coming to the meshing, before you turn your CAD model to a CNC model, you need to put it through a slicing software. ఇదంతా కట్ చేయాలి. So coming to the mesh density, before CAD model gets into your 3D printer as a CNC program, it has to go through a slicing software. And this slicing software is usually this slicing software usually accepts a mesh model, which is usually a HTL file. So if you see the three different mesh models, both the three are all the three are of same sphere, but the mesh size is different. So if you have low mesh size, these rectangles which are big and prominent will be visible on your physical model also. So these very low mesh size is not allowed. If you go to very high density mesh, it may be possible that the data is so large that your slicing software will not be able to accept it. So usually we consider a medium mesh density which will accept the slicing software, and your 3D print will also be of good quality. So as you have gone through different aspects of designs of 3D printing, I would suggest that you download a HTL file which is available on any 3 which is available on any 3D printing or HTL files websites like in Printables or Thingiverse. Go for this overall test or overall 3D printer test and have a printout of it on your printer with your own settings. Once it gets printed out, you will get to know what features are printing good and what features are printing bad. For example, if there is no problem in these areas of 10 degrees, 20 degrees and 30 degrees, you can print overhang up to 30 degrees. If even you are getting up to 30, 40 or 50 degrees, you can see that your printer is good and you can go to overhang up to 40. And if you are lucky enough or your printer is that good, it can print a overhang up to 80 degrees. Usually it's not possible, but try to print this and you'll have different features that will be tested on this print, and you will know what are the limitations of your particular printer. So we have towers, you have overhangs, holes, vertical pins, and all features that I have mentioned in the class on this print. And if you print this, you will have a clear understanding of what your printer is capable of and what are the limitations of your print. You can put these limitations into your design so that you every time you get a good 3D print. In the next part of the class, I'll be discussing about the defects of the 3D print. Let's have a short break. We'll be coming back after a short break. Thank you. Welcome back to the session. Today we'll be in the next part of the session, we'll be discussing about various defects that happen in 3D printer. Understanding the defects will give you what are the parameters that affect the 3D print and its finish. So there are n number of parameters that need to be discussed individually. So better understanding of the defects that come in will give you the better understanding of the 3D printer. So let's get into the various defects. As you can see on the screen, there are various defects. I'm giving you very few of these 3D printing defects. There are many more, and many more keeps on crapping in. The first defect is your elephant foot, wherein the bottom layer is slightly expanded. The bottom layer is slightly expanded. When the print has to be a sharp corner, it will be a lightly expanded towards the bottom. This will affect the finish of your print and also the meshing of your print. So this print, this defect usually occurs due to the gap between your nozzle and the bed. If the distance between the nozzle and the bed is too low, if the distance between the nozzle and the bed is too low, this kind of defect is usually observed. That is why it is usually suggested to maintain this gap between the nozzle and the bed to at least the layer thickness that you are giving. The layer thickness is also depending on your finish, but it's usually preferred like you need to give the distance between the nozzle and the print equal to the layer thickness. There might be a chance of one more defect due to this gap. If the gap between the nozzle and the bed is more than the layer thickness, it may cause wrapping, wherein a part of the 3D print is, as you can see, there is one more defect that happens due to the gap between the nozzle and the bed is not maintained, is the wrapping, wherein as you can see, a part of the print is getting contracted towards one side due to the lack of strength or lack of bonding between the bed and the print material. So if the print material and the bed are tightly bound, this kind of defect, which is wrapping, is not found. This is found if the bed is, or the 3D print or the 3D print material is not attached to the bed properly. So if the distance between the bed and the nozzle is more than the distance required, then the wrapping occurs. The next defect is the layer shifting. Layer shifting occurs due to incorrect extruder position. This might be occurring due to a slip, a tight belt, or the loose belt. In either cases, the layer shifting may occur. And there might be a chance of bed, which is on the 3D printer, which is also moving. So shaky bed or loose or over tight belt may cause this problem. So we need to keep in mind that the belt tension is adjusted, and your bed is firmly fixed to your 3D printer before giving the print. The next print that you can see is under extrusion, or the next defect that you can see is the under extrusion. Under extrusion happens due to low extruder temperature or low extrusion multiplier. So this is the nozzle property that you can change in your settings, and these are also nozzle property which you can change in the settings. So how can I eradicate it? Just increase the nozzle temperature. Sure. Or reduce the, sorry, increase the extrusion multiplier. So the next defect that we can observe is the layer delamination, wherein this is observed where the material will have high shrinkage. So this is the material property that you are using. There are various materials, and usually ABS, TPU will have this high shrinkage. This might also happen due to insufficient extruder or bed temperature. This may also happen due to excessive fanning or cooling it. So So as you can see, there is the bond between the layers here is broken due to the stresses which are created due to high shrinkage. So this particular defect between the layers here is definitely due to the shrinkage, whereas this particular gap is created due to the low this particular gap is maintained due to the insufficient bed temperature. So there might be these these are all the reasons for the layer delamination. So how to avoid this layer delamination? So usually material with high shrinkage need to have controlled ambient temperature. So usually 3D printers with casings are used to keep the ambient temperature constant. Next, controlled cooling and avoid cross current winds. And last but not least, increase the extruder temperature, reduce the extruder temperature. Increase the extruder temperature the temperature by 5 degrees. So next effect is the over, over extrusion. So as in the case of under extrusion, the opposite that can happen is the over extrusion. This happens for the same reasons as the under extrusion. One is high extruder temperature, and the second one is high extrusion multiplier. Simple correction in these parameters, that is reduce the temperature and reducing the multiplier will reduce the temperature, reduce this defect. The next important thing is your stringing, or the most seen or the popular or most notorious 3D defects or usually is the stringing. The stringing happens as you say, as I've told you, like this particular extruder will put in and put out this filament from the nozzle when it's required and when it is not. There might be a small error in this extraction process wherein a small amount of filament, that is fused filament, is deposited near the filament, near the filament, and due to this stringing process happens. So if you increase the retraction rate, this particular stringing can be reduced. So stringing is usually happening due to the retraction or the retraction settings, and if you increase the retraction settings, the stringing can be reduced. Next one is the ghosting or the ringing. As I have told you that due to the inertia, the vibrations in the 3D printer can be increasing. As the vibration increases, you can see there is quite a chance that there are some ghost lines along the features that need to be printed. So to avoid this, you can just reduce the printers, or you can need to check for any loose parts or loose ends on your 3D print. The last but not least is the Z wobble. This is due to the vibration in the Z axis, or if your Z axis spindle is not lubricated enough, wherein the Z axis, if the Z axis is not moving as it has to move, this kind of Z wobble is observed. The next one is the clogging or incomplete print when the temperatures of the nozzle is less, or there is some obstruction in the nozzles, or the clogged nozzle may give you this incomplete print. So this can be irrigated using by maintaining your nozzle, maintaining your bottom tube, or giving uh, or changing it timely. So these are the defects that I wanted to cover today. We have covered the various aspects for the design, and we have understood what are the parameters that will affect the quality of your print. Thank you for your patience listening. Thank you.